Imagine for a moment that everything you are used to is gone. No central heating, no solid concrete walls, no double-glazed windows and mineral wool insulation, and outside the window, not just winter, but merciless, primal cold, which penetrates through every crevice and seems to want to freeze the very soul. Welcome to the world of a medieval English peasant who had to build himself a house, not for comfort, but for survival. We imagine their dwelling as a primitive, windswept hovel of sticks and mud, where people huddled together in desperation around a smoldering fire. But what if I told you that this picture is only half true? What if this seeming primitiveness hides a story of incredible, brilliant engineering? A story of how our ancestors, with nothing of our technology, created their own, amazingly efficient counterparts. This story will take you not just to a village, but to a medieval construction site, where every element of a house was not just a detail, but part of a complex system of survival. This is the story of how, using only an axe, clay, dung, and knowledge of nature, people built houses that were at the same time a dwelling, a heater, a refrigerator, and even an air defense system against disease. Instead of earthquake-proof foundations, they had a floating frame. Instead of breathable membranes, they had living walls. Instead of a floor heating system, they had self-heating compost underfoot. Today we'll reveal 10 of the most complex and unexpected construction life hacks that transformed a simple shack into a high-tech, by the standards of its time, survival machine. We'll constantly compare their methods with our modern techniques, and you'll be amazed at how much the principles of energy efficiency and sustainable building remain the same. Are you ready to learn that the medieval house was not just a box, but an intelligent living organism? Then let's get started. Any modern construction, from a skyscraper to a summer house, starts with a foundation, a solid, concrete, steel-reinforced base that goes into the ground below the freezing point. This is axiomatic. It is necessary for the house to stand stable and not to crack when the ground freezes in winter, swells from water expanding into ice, and in spring settles, turning into a squelching mess. The medieval peasant, of course, had neither concrete nor an excavator, nor the ability to dig deep pits. But they had the same problem, and it was far more serious. The damp clay soil of England froze and walked very hard. The silent, titanic force of frost heaving can break stone and bend steel. Any house standing rigidly on it, dug into the ground, would inevitably be torn apart in a few seasons. Its walls would crack and its doors would stop closing. And they invented an ingenious, counterintuitive solution. Their houses didn't have foundations as we know them. They had their own version of a modern earthquake-resistant foundation on damped piers, designed to protect buildings from earthquakes. The main structure of a farmhouse, especially in the wooded areas of England, was not a log cabin, but a frame. The most widespread and ancient type was the so-called cruck frame. It was based not on vertical posts, but on giant, naturally curved oak logs, which, joined at the top, formed an A-shaped arch, like the ribs of a giant whale. These arches, set in a row, carried the entire colossal weight of the roof. And most importantly, most ingenious, these massive, multi-ton logs were not dug into the ground. Their bases, or heels, were set on large, flat boulder stones, which simply lay on the leveled surface of the ground. What was the genius of this solution? The house was not rigidly tied to the ground. It floated on it. When in winter, frost heaving raised the soil unevenly, the house, like a ship on a slow, mighty wave, just slightly lifted and swayed together with the supporting stones. In spring, when the earth settled, it would sink just as smoothly. The entire structure was flexible and movable. It did not resist the forces of nature, but followed them. This prevented critical stresses in the supporting frame, saving it from cracking and collapse. It was a passive but incredibly effective system for adapting to unstable ground. Modern engineers use a similar principle of damping and decoupling the building from the foundation to protect it from seismic shocks. The medieval carpenter, not knowing these words, arrived at the same solution intuitively. In addition, stone supports solved another major problem: rotting, the main enemy of any wooden building. Wood in constant contact with damp earth rots in a few years, even if it is a mighty oak. The stone shoe worked as a modern foundation waterproofing. It cut off capillary moisture infiltration, lifting the precious, hard-worked wood above the damp earth and allowing it to be constantly ventilated. This increased the service life of the supporting frame not by decades, but by centuries. Finding and hauling these boulders to the building site, using only levers, ropes, and perhaps oxen, was the hardest labor for the entire community. But it was a major investment in the longevity and stability of their home. This was the first and foremost secret of their homes. Not to fight the forces of nature, but to adapt to them, using flexibility instead of rigidity. If the foundation was the hidden mind of the house, then its heart, skeleton, and its whole essence was the frame. And it was not just a set of beams, but a real work of carpentry art, a complex spatial structure, comparable in its engineering logic and efficiency to a modern load-bearing exoskeleton of a building made of laminated timber or high-strength steel trusses. As we have already mentioned, the basis was often cracky, paired curved oak logs. Finding two mighty oaks in the forest that had grown with an almost identical curve under the influence of wind and light was in itself a great fortune and required a deep, almost mystical knowledge of the forest. The master carpenter, the Wright, one of the most respected figures in the village, was in charge. He could wander the forest for weeks, searching for suitable trees, seeing in their living trunks the future ribs of the house. The trees were cut in winter, when the movement of sap in the trunk is minimal, and the wood is the densest and most resistant to cracking. Then began the hellish, months-long labor. Using only an axe for rough work and a cleaver, a special axe with a blade perpendicular to the handle, for finishing, the carpenter had to carve two perfectly symmetrical, smooth curved beams from round, uneven logs. But the most complicated and ingenious thing was ahead, connecting the frame elements. They had no steel nails, bolts, or metal plates. All joints, hundreds of joints in one house, were made exclusively of wood on the principle of tongue and groove, or as it is also called, dovetail. These are the most complicated carpenter's locks, where at the end of one beam, a ledge, spike, was cut with jeweler's precision, and in the other, a recess, groove, corresponding to its shape and size. The parts had to fit together with millimeter accuracy, like parts of a Swiss watch. Too loose a joint made the frame wobbly, too tight a joint could split the wood as it dried. The connection was fixed not with nails but with wooden nails, large, thick nails made of dried, hard wood, oak or ash, which were forcefully hammered into the holes pre-drilled with a hand drill. The dry dowel swelled slightly when it hit the wet wood of the frame, creating an incredibly strong, monolithic joint. Such a frame was incredibly strong and elastic at the same time. It could withstand the huge weight of a heavy thatched roof in hurricane winds, slightly playing and cushioning the loads unlike the rigid and fragile masonry. The whole house was assembled on the ground, on a special flat area, like a giant 3D puzzle or a Lego constructor for adults. Each piece was carefully fitted and then numbered with special notches or Roman numerals so that nothing would get mixed up in the final assembly. This is exactly like the modern system of marking parts in production. And then came the main day, the day of lifting the frame. The whole village would gather for it. It was not just labor, but a celebration known as raising B. Using long poles, levers, ropes, and the pure muscle power of dozens of men, under the rhythmic shouts of the master carpenter, they slowly, with bated breath, lifted the first multi-ton A-shaped truss and set it on the supporting stones. This moment was accompanied by universal jubilation. Then the rest of the trusses were lifted, connecting them with longitudinal beams. This celebration of collective work, where everyone helped everyone else, ended with a common feast, symbolizing the unity and strength of the community. The frame was practically eternal. The walls could crumble, the roof could leak, but the mighty oak skeleton, blackened by time and smoke, could stand for centuries. Even today in England, there are still buildings built with this technology 600, 700 years ago. It wasn't just building. It was the creation of a family heirloom, a house that will serve your children, grandchildren, and great-grandchildren, becoming a silent witness to the history of an entire family. After the majestic skeleton of the house was installed, it was necessary to build the meat on it, to erect the walls. And here we are in for another technological surprise. The walls of the peasant house were not solid and airtight. They were not analogous to our brick, block, or concrete walls that completely insulate us from the outside environment. They were analogous to a modern, high-tech, breathable membrane like Tyvek or Gore-Tex, which protects against wind and rain, but allows the house to breathe, letting out excess moisture and creating a healthy microclimate. The technology, which is thousands of years old, was called wattle-and-daub. Vertical posts made of thinner logs were inserted between the massive beams of the frame in specially cut grooves, and between them, a dense lattice of flexible and strong twigs of hazel, willow, or ash was created. The rods were woven vertically and horizontally, as in a giant basket, creating a strong but flexible and lightweight base. This was their analog to the modern reinforcing mesh on which plaster is applied. Then this wicker base was covered on both sides with a special composition, mazanka, and it was not just clay diluted with water. It was a complex, carefully selected composite material, their own environmentally friendly bioconcrete. The composition included clay as the main binder, river sand for strength and to reduce shrinkage, chopped straw, hay, or even horsehair for internal reinforcement, like the fibers in modern fiber concrete, which prevent cracking when drying. And this is the most important and unexpected component, fresh cow manure. To us, manure is waste. To them, it was a valuable building material. Manure had several critical functions at once. First, its undigested fibrous structure served as an additional reinforcing element. Second, the chemicals and enzymes it contained made the clay mixture more malleable, sticky, and water-resistant after drying, working as a natural plasticizer. Third, ammonia and other compounds worked as a powerful natural antiseptic, preventing the growth of mold and mildew inside the wall. But the most important property of such a wall is its vapor permeability. In winter, a huge amount of moisture was formed inside the cramped hut from people's breathing, cooking, and, as we will see further on, the presence of animals. In a house with our modern sealed walls and double-glazed windows, this moisture would immediately condense on cold surfaces, causing streams on windows, dampness, black mold, and respiratory illnesses. But the wattle-and-daub wall allowed this moisture to slowly seep outward in the form of vapor, keeping the inside relatively dry and healthy. The house breathed, getting rid of excess moisture on its own. This was an ingenious solution to the problem of condensation, which today is dealt with by complex and expensive forced ventilation systems and vapor barrier films. Their house was a living, breathing organism that regulated its own humidity, ensuring a healthy life for its inhabitants. One of the most shocking for modern man, but also the most ingenious and effective survival technologies, was the integration of living space with the stable. We are used to a clear, almost sacred separation. Here is a clean, warm house for people, and here is a separate, cold barn for livestock. But in the medieval longhouse, the main form of peasant housing in Northern Europe, there was often no such separation. It was their equivalent of a modern, energy-efficient house with an integrated heating system powered by biofuel. Only the biofuel was the animals themselves. The longhouse was an elongated, rectangular structure under one common, massive roof. The interior space was divided, not by walls, but functionally. One end of the house, usually the one with the hearth, was the family's living area, their living room, bedroom, and kitchen at the same time. The other end, often separated only by a light wooden partition, a wattle, or simply a trough, was the winter stall for the most valuable livestock, 1 or 2 dairy cows, a few sheep, perhaps a pig and piglets. It wasn't because of laziness, lack of space, or untidiness. It was an elaborate, centuries-old strategy of thermoregulation. A large herbivore, like a cow, is a walking, self-regulating stove. Her body temperature is about 38.5 degrees. In the process of digesting coarse plant food, the cow's complex, multi-chambered stomach, which acts as a biological fermentation reactor, generates enormous amounts of heat. According to modern calculations, one cow at rest generates as much heat as a kilowatt electric heater. This heat from several large animals in the same confined space greatly increased the overall temperature of the hut, especially at night. If it was -20 outside, the temperature inside, even with the hearth out, could stay above zero. Thus, the animals were a constant, free, and fully autonomous source of heating, which worked all night long when the main hearth was out. Of course, the price for such biological heating was high, and we would have found it unbearable. It was a constant background noise, the measured chewing of gum, sniffing, snorting, quiet mooing. It was a peculiar, thick and heavy odor. The pungent smell of ammonia from urine mingled with the sweet smell of stale hay and the earthy perfume of manure. It was also completely unsanitary. The risk of disease transmission from animals to humans, from skin parasites like lice and ticks to brucellosis or anthrax, was enormous. But for the medieval peasant, it was a reasonable and the only possible compromise. The smells were the familiar odors of life and rural prosperity, and the warmth the animals provided was the difference between life and an agonizing death from hypothermia and sleep. Moreover, such an organization of life had other practical advantages. The proximity to the livestock ensured their safety from wolves, which came close to the villages in winter, and from thieves. It also allowed women to milk a cow or a goat without going out into the bitter cold right inside the house. Children often slept snuggled against the warm flanks of lambs or calves, protected and warmed by their warmth. It was a closed, completely symbiotic world where people and animals warmed each other, sharing the same roof and the same fate. The roof was the most important element of the house, its main shield against cold, penetrating winds, rain, and snow. And it was also a true marvel of medieval engineering. It was not just a thatched roof, but a complex, multifunctional, smart system that combined the functions of high-performance insulation, breathable waterproofing, and even industrial equipment for food preservation. As a rule, the roof was covered with a very thick, up to half a meter or more, layer of reeds or long-stemmed rye, which were laid according to a special, centuries-old technology. This layer was their analog of modern insulation from polystyrene foam or mineral wool. Hollow plant stems contained a huge amount of still air, which is known to be the best natural heat insulator. Such a thick plant coat reliably protected the house from heat loss through the roof because it is upwards that the main heat in any room escapes. The heat from the hearth, the animals, and the people themselves did not escape instantly, but lingered under this massive insulation. But how did such a roof protect against the constant English rain? The genius was in the laying technology. The stalks were laid very tightly in bunches at an acute angle, at least 45-50 degrees. Water rolling down the smooth outer surfaces of the stalks simply did not have time to seep inside. It was their version of a modern pitched roof with perfect waterproofing, and if any moisture did penetrate into the upper layers, it was retained there without reaching the living space, and then dried up thanks to natural ventilation. The roof breathed while remaining dry inside. But the most unexpected and ingenious upgrade the roof received from the inside. As we remember, the hut had no chimney. The smoke from the hearth, hot and saturated with chemicals, would rise up and slowly seep through the thickness of thatch. This process was their own system of fungicidal, insecticidal, and hydrophobic treatment of the material. The smoke contained creosote, phenols, formaldehyde, and acetic acid. These substances settled on the straws, soaking them through. This made the straw completely unpalatable and poisonous to bacteria and fungi, preventing rotting. The resinous deposit made the straw more water-resistant, and the acrid odor deterred insect pests, mice and birds that could nest in the roof. As a result, the roof, which in normal conditions would have rotted in 5 to 7 years, in such a smoked condition could serve for up to 50 years, requiring only minor cosmetic repairs. Moreover, this same smoky, warm space under the roof served as an ideal smokehouse and drying closet. On the wooden beams, in the smoke itself, on special hooks were hung what was to be stored for a long time: pork hams after the fall slaughter, strips of salted bacon, rings of blood sausage, bundles of gutted and salted fish. bundles of medicinal herbs. The products were slowly smoked in aromatic wood smoke, and this process was their analog to modern canning technology. The smoke, firstly, slowly dehydrated the surface of the product, creating a dense protective crust. Secondly, its chemical components, the same phenols, penetrated deep into the meat, killing bacteria and preventing spoilage. Thus, meat and fish acquired not only a characteristic pleasant flavor, but also the ability to be stored for months until spring. The whole hut worked as one big multifunctional smoking chamber, where both food and the dwelling itself were preserved at the same time. In our modern homes, the main source of heat is usually radiators against the walls or a beautiful but inefficient fireplace. A fireplace, for all its romanticism, is essentially ventilation working in reverse. Most of the heat, up to 80%, escapes into the chimney, and for combustion it sucks cold air from the street into the house. The medieval peasant didn't have a fireplace. He had an open hearth right in the center of the only room, and this, paradoxically, was a much smarter and more efficient solution. Their hearth was the equivalent of a modern, powerful circular infrared heater. The hearth was simply a stone or clay-lined platform on an earthen floor. The fire burning in the center of the room radiated heat in all directions, 360 degrees. It evenly warmed not so much the air, which according to the laws of physics was rising up anyway, as the surrounding objects, the earthen floor, the clay walls, the wooden beds, and most importantly, the bodies of the people sitting around it. This radiant infrared heat, like the sun's heat, penetrated deeply and warmed much better and more efficiently than just the warm air from a convector. The person felt comfortable even when the room temperature was relatively low. The family's entire life in winter literally revolved around this central living fire. It was their sacred place, their altar, their analog of the modern kitchen, living room, and office in one person. Here, in a cauldron suspended on a hook above the fire, all food was cooked. Here, by the light of the dancing flames, they gathered in the long, dark evenings to do small jobs. Men mended harnesses, women spun wool. Here they told stories and sang songs. Here, around the cooling but still warm coals, the whole family slept on their straw bunks. The main problem, of course, was the smoke. It filled the whole room before finding its way out through a special hole in the roof. Life in such a hut was life in a constant light haze. The smoke ate the eyes, caused constant coughing, and all surfaces were covered with a layer of black, greasy soot. But as we already know, the peasants learned to control this process and even benefit from it. They used green wood to create a warm cushion of smoke under the ceiling that kept the cold air down. They sat and slept low, near the floor where the air was the cleanest and warmest. They knew which kinds of wood gave less smoke and which gave more flavor. Living in smoke was the price they paid for the most efficient and economical heating possible. The central hearth was the pulsating heart of the house, which warmed everyone without exception, making no distinction between honorable places by the fire and uncomfortable corners, as is the case with a fireplace. A modern home, a symbol of our well-being, cannot be imagined without large, bright panoramic windows. We appreciate the view, the natural light, the feeling of being one with nature. But for the medieval peasant, whose life was an annual war with the cold, the window was not a source of joy, but a major gap in the defense, a strategic vulnerability. Every hole in the wall, even the smallest, was a hole through which precious, hard-won heat escaped. The glass, murky, imperfect, and bubbly, was incredibly expensive, equivalent in cost to an entire cow, and available only for churches and lords' castles. So the peasant house was essentially an airtight fortress built for defense against the cold, and its windows were more like loopholes in a castle wall. This was their version of extreme, uncompromising energy conservation. Usually there were only one or two, at most three tiny holes in the hut, no bigger than a human head, and their arrangement was not chaotic, but strictly thought out. One, the larger one, usually faced south to catch the meager rays of the low winter sun. The other, smaller, was on the leeward side, most often on the eastern side, and served through ventilation when it was necessary to expel thick smoke from the hearth from the room in a few minutes. These openings were not empty. Their glazing is another example of astonishing ingenuity, using improvised materials that were their counterpart of modern frosted or translucent polycarbonate panels. The best and most expensive option for the peasant was finely wrought, cleaned and stretched on a wooden frame, an ox or cow bladder. It was thoroughly washed, scraped, and then stretched and dried until it became thin and translucent. Such glazing let in quite a lot of diffused, soft light, but at the same time was surprisingly strong, flexible, and well protected from wind and rain. Another more common option was thin plates of horn. The horns of cows and bulls were boiled in boiling water for a long time until they became soft and malleable like clay. They were then split and pressed between two heavy flat stones. The result was cloudy, yellowish plates that let in less light but were more durable and stronger than bullseye. This was their counterpart to the shatterproof but less light-permeable acrylic glass. The cheapest and most common option, however, was a simple linen cloth that was soaked in boiling linseed oil or melted animal fat. Once dry, the cloth became translucent and waterproof, working like oiled paper in traditional Japanese homes. It gave off very little light but provided reliable protection from the wind. These openings were closed at night. This was an essential part of the ritual of keeping warm. From the inside, they were closed with tight-fitting wooden shutters, and all the gaps were carefully plugged with bundles of dry moss, straw, or old rags. This was their analog of modern energy-saving roller shutters or airtight triple-glazed windows. The peasant was constantly, every day, looking for a balance between light and warmth. To live in semi-darkness by the light of the hearth and the beam was immeasurably better than to freeze to death in a bright but cold house. This approach, minimal window openings, the use of translucent materials instead of transparent ones, and reliable nighttime insulation, is one of the key principles of the modern passive house, an architectural standard that aims to maximize energy conservation and minimize heat loss. The floor of the peasant hut was another amazing and multifunctional element of a complex survival system. It was not just a trampled earthen floor, as we might think. It was a multi-layered, living floor that would eventually evolve into their own analog of a geothermal heated floor heating system, where the heat source was pure biochemistry. The floor was indeed based on compacted earth or clay, but on it a thick layer, several tens of centimeters, was laid a bedding of any available organic materials: straw, reeds, ferns, heather, dry leaves. This layer served first as insulation from the cold earth, and second, to create relative softness and comfort. But its primary function was different. It was fuel for the bioreactor. As we remember, cattle were often kept in one part of the house. Animal waste, dung and urine, was mixed with straw bedding. People did not always go outside in the bitter cold or storms either. Small food scraps, garbage, all this was left on the floor and trampled on by feet. Over time, this lower, moist, organic, and bacteria-rich layer of bedding turned into a slowly rotting, composting mass. The process of aerobic decomposition of organic matter, or composting, which we use today in our dachas to produce fertilizer, is an exothermic reaction, i.e., a reaction with the release of huge amounts of heat. Billions of bacteria, breaking down organic matter, work like microscopic stoves. Inside this heaped, damp mass, protected from above by a layer of dry straw, the temperature could rise to 30, 40, and sometimes 50 degrees. This slow but constant and totally free heat source heated the floor from the inside out, 24 hours a day. It was their natural geothermal heating system powered by waste products. Of course, this had obvious downsides, a specific odor, and complete unsanitation from our point of view. But the peasants solved this problem by regularly adding a new, clean and dry layer of straw or reeds on top, which insulated them from dirt and absorbed odors. This multi-layered cake was warm and dry on the surface, while invisible processes were going on deep inside, generating precious heat. In the spring, all that months of compost was shoveled out of the hut and became invaluable, the best fertilizer for the fields, ensuring future harvests. It was another example of an ingenious closed cycle where what we think of as garbage and waste was transformed into a valuable resource, first into heat and then into food. The peasant house was essentially a one-room house. It was a single, elongated space where the family lived, worked, and slept. But that doesn't mean that all of this space was equally cold. Using the simplest and most affordable means available, they created multiple microclimates within this one large room, implementing what we would today call an advanced climate control zoning system. Their main goal was not to heat the whole house, but to create small, warm islands of life inside the cold ocean. The main tool for this zoning was heavy curtains. These were not light curtains. They could be coarse, thick, felted woolen blankets, old stiff cow or deer skins, or dense mats woven from burlap. These curtains were hung from the ceiling beams, separating the sleeping area, usually located farthest from the entrance and closest to the hearth from the rest of the space. At night, the whole family would gather in this partitioned nook. The curtain down to the floor cut off drafts and created an enclosed small volume of air. The space was very small, and the heat from the breathing of a few people, as well as the residual heat from their bodies, was enough to raise the temperature several critical degrees over the rest of the hut. The curtain kept that heat from dissipating throughout the room. Essentially, they built a tent inside the house, creating a multi-layered insulation system. This was much more efficient and economical than trying to heat the entire hut. The bed, if there was one, was also part of the system. Often it was not just a bed, but a so-called box bed, essentially a large wooden box with a roof and sliding doors or thick curtains. The whole family could sleep inside this box, and their shared warmth created an incredibly cozy and warm microclimate, even if the cabin itself was in sub-zero temperatures. It was their version of a personal sleeping pod with individual climate control. Doors also played a crucial role in zoning. They were always made very low and narrow. A modern tall person would have to bend over a lot to get in. This was not because of the short stature of our ancestors, but to minimize heat loss. Smaller doorway area means less icy air rushing in every time you open the door. Often the door was double, an outer and an inner door, with a small vestibule in between, which worked like a modern supermarket thermal airlock, cutting off the cold street air from the warm inner air. This clever zoning of space allowed them to make the most efficient use of any heat source, be it hearth, animals, or their own bodies. They did not waste precious energy heating unused areas, concentrating heat where it was needed most, in the sleeping and resting area. Finally, the most difficult, the most unobvious, but perhaps the most important aspect of building a medieval house is what happened even before the first stone was laid or the first tree cut down. It was planning. The medieval peasant, not knowing the words architecture, thermodynamics, and engineering, intuitively, based on the centuries-old experience of his ancestors, followed all the basic principles of the modern passive house, an advanced standard of energy-efficient construction that seeks to minimize energy consumption for heating and cooling. The choice of location for the house was critical. It was never built on a hilltop, exposed to the winds, or in a damp lowland where heavy cold air and fog accumulated at night. The ideal location was on the southern or southeastern slope of a hill that was protected to the north and west, the sides from which the prevailing cold winds blew, by a forest, another hill, or even just a bend in the terrain. This arrangement provided maximum precious sunlight and natural protection from the wind. The orientation of the house on the sides of the world was also not accidental. The long axis of the house was almost always extended from west to east. Thus, one of the long walls of the house, the largest in area, faced south. This was their version of a passive solar collector. In winter, when the sun is low above the horizon, its rays fell on this wall throughout the short day, warming it. Small windows on the same wall allowed sunlight to penetrate deep inside and heat the earthen floor, which then slowly gave up heat at night. The wide overhanging thatched roof worked as a natural canopy, which in summer, when the sun was high, conversely shaded the south wall, protecting the house from overheating. The narrowest end wall, often with no windows or doors at all, always faced north or northwest, taking the brunt of the icy wind. The location of the entrance was another trick. The door was almost never made on the windward, northern side. It was placed on the south or east side, often under the protection of a specially built simple canopy or in a natural niche. The surrounding trees were also part of this complex ecosystem. Deciduous trees, such as oak or maple, planted on the south side of the house, provided dense shade in summer, and in winter, shedding their leaves did not prevent sunlight from entering the house. And dense evergreen spruce or pine trees planted in a dense group on the north side served as a natural evergreen windscreen that reduced wind speed and reduced convective heat loss from the hut by 20–30%. All of these techniques, proper orientation, use of topography, natural windbreaks, thoughtful placement of windows, worked together to create a house that was in perfect harmony with its surroundings. It was not just an object roughly placed on the ground, but a complex system integrated into the landscape, which used the forces of nature, the sun and the wind, for its own benefit. And this deep, intuitive understanding of their world was the main secret of their sustainability and survival. So we made a journey deep into medieval engineering, taking apart an ordinary peasant house by logs and lumps of clay. And what did we see? Not a primitive, windswept hovel, but a true miracle of adaptation. A complex, multifunctional survival machine where every element was not what it seemed at first glance and performed several vital functions at once. We learned that instead of a concrete foundation, they had a flexible, rock-floating structure, their own version of an earthquake-resistant platform, that their walls of twigs and dung worked like a high-tech breathable membrane, protecting against dampness better than many modern materials, that their floor was not just a floor, but a geothermally heated bioreactor turning waste into precious heat. We realized that their central hearth was not just a campfire, but an efficient infrared heater, and that its smoke was an integrated defense system that preserved both home and food. Their tiny clerestory windows were a model of extreme energy conservation, and the entire house, properly oriented with the sun and wind, was a perfect passive house, built hundreds of years before the concept was invented. If you were interested in this journey into the past and you have a new look at what is home, put a like and subscribe to our channel. There are many more amazing stories about the ingenious ideas of our ancestors to come. And in the comments, which of these building secrets struck you the most? And what other aspect of medieval life, be it clothing, medicine, or agriculture, would you like to learn about next time?